Hello, everyone here. So hopefully you are enjoying your July of the 4th week this week, and hopefully you are meeting many of your friends and attending a lot of fun activities, like going to the ocean shore to see the tsunami relics. Probably that's a good way to celebrate the July the 4th. All right, so last week we already talked about the Laplace experiments and some fundamental concepts about probability. So this week we are really going to talk about axioms of probability. That's really about what some more concepts and the definitions about probability. So first, the first definition we're going to see is the probability measure on a finite sample space. Finite sample space here means like the omega is a finite set. So for example, it cannot be the set of the natural numbers because natural number is an infinite set, although it is like it's a countable set, but it's infinite. So let omega be a finite sample space. And the fancy here is a collection of all subsets of omega, and the probability measure on this this is not a triplet. This is a two element list. It's a function p from fancy to real numbers. What does a function mean here? A function is yeah, you can just assume it's a process of like assigning every element inside the set of fancy A with one specific number in real numbers. But for probability measure, it must satisfy these three properties. The first one is like for all the events in this fancy or the power set, the probability must be greater than 0. And also for the probability of the sample space, the omega is equal to 1. And the third property is that if the two events are pairwise disjoint, pairwise disjoint is which means for two sets, those two sets are like have no relation, have no overlap with each other. So it's pairwise disjoint. And in this case, the union of those sets probability is the same as the addition of each of this event. So here the number PA is also called the probability that event A occurs. So this is how we read this notation. And so why these three properties must be satisfied? So what's an intuition for that? The first is the non-negativity. So why all the probability must be like non-negative numbers? For example, if you want to measure the distance in real world, in real world, it must be like have 1 meter, 0 meter, but it cannot have like negative 1 meter. So that is not realistic. And the probability is a study for reveal the realistic problem. So it satisfies the non-negativity. And also for the second property here, the probability of the omega is equal to 1. So what does that implies? So that's a normalization. We want to say, okay, if one thing actually happens, so happens with no doubt, happens for sure, it will be equal to 1. So this is a normalization, and we do that also in many cases. Like when if you take the calculus class before, when we are like calculate the vectors, we want to find the unit vector, and the unit vector here is another way of normalization. So first, the third one is it says it's a additivity. This means if you have like, for example, you have an orange and you cut it into half, but the amount of the volume that you have is the same as the one whole orange. So you can cut it in 3 pieces, but the total volume is still be the same. So that's the additivity of the orange. And here it's represented by this formula. All right. And I want to introduce another new definition too, is the sigma algebra. Sigma algebra is a very interesting topic in algebra. And this is not really have many interpretation in reality, but it is just a type of number that has these 3 properties. First one is like the empty set must be in this set. And the second one, if one element belongs to this set, then this element's complement is also belongs to the set we're studying. This is called closed under complement, which means like if one set is inside, so the complement is also inside. And the third one might be first look very hard to interpret what's going on. So it's just says like A1, A2, A3, maybe A4 to A billion is belong to this the set we are studying. This is a collection of all subsets of certain sample space. So and this notation means the union of all sets. This does not mean that it's a union of A1 to A billion. For example, if here is A1 to A billion, this is not that meaning. It means A1 union A2 is also in that set, and A1 union A2 union A3 is also in that set. It just means no matter how many sets there are, all of the ways of the combination of the union sets are also in this in the set we're studying. And if one collection of subsets satisfy these three properties, then we say it is a sigma algebra here. So let's start with a very simple example. Like based on the mathematicians ever found, the smallest sigma algebra associated with a given sample space is a set with two elements, the empty set and the sample space, which is a whole set here. So so first, how do we want to prove this statement? So usually if we are given a lot of properties of a certain concept, like here we have three properties, a good way to start the proving process is to ask yourself whether each of these three properties are satisfied. So first, let's ask if the empty set is in the fancy A, is that right? Oh yeah, it is in that. So the first property satisfied. Then we ask if the second property satisfied. Is that the case? Maybe yes, because if we pick the empty set here as the set and its complement will be the sample space. So here is, which means that the complement is also inside, and we take the sample space as our original set, then the complement is the empty set, which is also in fancy. So the second one satisfied. So the only block we want to pass by is to prove the third property is correct. This is also not very difficult in this question, because we just want to show the union of the empty set and the sample space is also inside fancy. And here it's very obvious because the union of an empty set with the sample space, just the sample space itself, and it's obviously inside fancy. So with these three properties, we already proved that this smallest sigma algebra is actually a sigma algebra. But someone may want to ask, like, if there is a smaller sigma algebra possible, that's a good question. And if you really want to find out that, it's a good research direction, I would say. But how to prove that how to prove that if there is a smaller sigma algebra? First, you want to show that there exists a set with only one element inside, and that can be a sigma algebra. Which is considerably hard, but that might happen. I really encourage you to explore. And one hint is that if the sample space is empty, so that's a hint for this problem. But that is not for general cases. It's just for the given omega here is empty set. And also, I want to prove another statement, which looks more complex. Here it says if the omega is finite, then the power set is a sigma algebra. And this is the notation of a power set. We talked about that before. It writes as a 2 to the power of omega. This is the power set. And we'll start the proving process. So first question is to ask if the empty set is belong to this one. And that's an obvious question because omega is a subset of any set. So that is proved. And for the second one, for any arbitrary set A inside the power set, is the complement of the set also in it? I'd like the first mind by reminding you to say yes, but why is that? This is because no matter the A and the complement of A, their union, or we say their union, their union is the same as the omega. So the power set contains any set that is a subset of it. So as a result, we can say the complement of the set A is also inside the that fancy A set, the power set. So second one is proved. And the third one, how to convince yourself, like if A1, A2, A3, A4 to A billion is inside the power set and their union is also inside. This is the first mind you thought is like all of the element inside those A1 to A billion is in the range of the omega. It cannot be out of the range because they are subsets. And as a result, if that's a subset of it, their union cannot have any new elements. It's just the elements of each of them. At most, each of them not have any elements beyond that, or it will not be a union set. So in this case, it is also smaller or equal to the set of the omega. So the union is definitely a subset of omega. So the three properties we have already proved. So here's a more advanced question: is if A is any subset of omega, is that set with 4 elements like the empty set, the sample space, and A complement A, is that a sigma algebra? That process will be very similar to this one, and I want to leave as an exercise for you to explore. And here we will see another example of a power set. So first we consider a set which is the constitute of 4 elements 1, 2, 3, 4, and want to see what's the power set of it. So the power set of it is 1, 2, 3, 4, 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4, 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4, and 1, 2, 3, 4, which is same as the sample space and the empty set. So give example here. If we want to set a set A as 1, 2, then the complement of C is the omega minus the set A, which is 3, 4. So that's a more realistic example to show what's the relation between those sets. So hopefully you already understand. And now we're going to the third definition we're exploring today. Is called the probability measures definition, or the general probability space. So if you remember, we already discussed a non-formal definition of probability in the first week. So now we will have a formal definition of probability. So after we already discussed about sigma algebra, the definition will illustrate as this one. And let the omega be a sample space, and the fancy A is a sigma algebra on the omega. A probability measure on omega fancy A is a function P from the fancy A to real numbers that satisfies three properties as well. So here the function also means like we assign a real number to each of the set, which of the element inside the fancy, which are all sets. And the first property is that the probability of A is greater or equal to 0 for all the element or for all the event, and also the omega, the probability of omega is equal to 1. And the third one is that it's not just for two A and B pairwise destroying event, but a collection of pairwise destroying event. It increases from 2-dimensional to n-dimensional. And here, if we say any of the two sets, like for example AJ and AK, if they are pairwise destroying inside this collection, and we say the whole set is pairwise destroying events, and if this happens, then the probability of the union of like all of the elements, all of the events inside this collection is equal to the sum of all of these events probability. And this might lead to one misunderstanding, which means if you have more sets, the probability will increase. But that is not the case, because for some events, the probability can equal to 0. So that is not that is with no doubt it can be 0. So if you add one more like event set into it, and the sum of the probability is still be the same, so they will never increase the probability. And also there's a new concept, it's called triplet. It's the probability triplet. It's the sample space plus the set of events and plus the probability measure, which is a function from the set of events to real numbers. These three properties, we combine them all together, is called a probability space, also known as the probability triplet we see before. So now we'll give you an example of coin toss. So here we take the sample space be like H and T, and of course in this question, the set of events are these 4 elements, and if we want to find a probability which is taken from the set of event to this range, because all of the probabilities is in this range, must be greater or equal to 0 and must be smaller or equal to 1. Or this is because if you have one event that is greater than 1, for example, you have 1.1, and because all other events must be greater or equal to 0, and you cannot decrease that value into 1 if you combine them, so the sum will never be 1. So this is the reason why we say it goes this function goes from like the fancy A to the range 0 and 1. And here the third element of this triplet is the probability measure. The probability measure for the empty set is 0, and let's say the success rate of toss ahead is P, then for head is P, and for T is 1 minus P, and for the sample space is 1. So what's the difference between the probability measure and the probability distribution? We can say just one thing we want to illustrate is the probability distribution must also be summed to 1. So if we pick the probability of H and probability of T, their sum is P plus 1 minus P, which is 1. So the probability distribution is all of the probability measure that's given to the simple event. The simple events is the events that have only one element inside it, which we already discussed last week. But if we add all of the the probability of a probability measure, it's 0.001 0 plus p plus 1 minus p plus 1. So here, well, the result is 2, which is not equal to 1. So the probability measure, the sum is equal to 1. This is not a guarantee. This is not a guarantee. Okay, and we'll also see another example here, which is more complex. And we say a die is thrown once. Notice that here we do not say it's a filled dice. So although we know it have 6 faces, but the probability for rolling each face is not the same. And here we'll say this the fence A is equal to the power set, and the property measure is given by for any event inside the sample space, the probability that event A happens is equal to the sum of all the simple events Pi. And here we already defined the Pi is P1, P2 to the P6, and they're all in the range of 0 to 1. And the property of A is the sum of all the event, sum of all the probability of Pi, which is a simple event that is belong to A. The I is belong to A. So this is same definition as the I would say yeah, as here. This is the same definition as here. So if the union of all the simple events is constructed to be A, and we need to sum them up together. So here we get this formula here. But if we imagine in another case that the die is fair, so the probability for each of the case happen is 1/6, and we can deal with this with our familiar Laplace experiment again. So the probability that A happens is the same as to say the cardinality of A over the cardinality of omega, which is 6. So that's in the case that the die is fair. And here we want to discuss some more properties about the probability measure. So let omega fancy P be a probability triplet, and A B belongs to the set of omega. And here the first property is that the probability of the complement of A is equal to 1 minus probability of A. This is not very hard to convince yourself, but if we want to prove that, it might be a little bit more difficult. So first we will say that by the definition of a complement, the omega is equal to A union with the complement of A. That is with no doubt, that's its definition. And also there's another property of the probability, that is, if two sets are equal, their probability is also equal. So here, because we have this equation, we can construct this equation here. So the probability of omega happens is the same as this union of the two sets happens. Now we want to introduce the probability, the property here, the property 2 here, which says the probability of the omega happens is always equal to 1. So here we can say 1 is assigned to this value and use property 3. The property 3 here, it means the union of many sets, the probability is equal to the sum of their probability. So we can write this term into this one, the sum of the two terms. And luckily, if we are going to here, we can remove all the things in between and just to say 1 is equal to PA plus PA complement. And here, if we move the PA to this way, it's the same as like the PA complement is equal to 1 minus PA, which we proved the property 1. So that's the whole process of the logical thinking behind this this proof. And we're also to see if we can prove the second property, that is if A is like it's a subset of B, then PA is smaller or equal to PA plus PB minus A. And this term is equal to PB. So this property has two parts. The first part is this inequality, and the second part is this equality. So we will deal with the inequality first. The inequality says if like because for every event, the probability of the event is greater or equal to 0. So obviously, the PB minus A is greater or equal to 0. So this indicates the PA was smaller or equal to the PA plus another like non-negative term. So here we already proved A. It's very simple. And prove B, PA plus PB minus A is equal to P. How we prove this one? So first we'll draw a graph here, like because A is a subset of B, like all of the elements that A contain, B must contain. So if we have this property here, we can note that if B is equal to the B minus A part, which is the blue part, union with A, and these two parts are pairwise, pairwise disjoint. This is because the reason we already said, like for all of the elements that A have B, or B must have that. So so finally we proved PB is equal to PB minus A union with A, which is the sum of those two terms, and we proved the second property. And for the third property, what if we want to say the property of like A union with B is equal to PA plus PB and minus the PA intersection with B? This is really fun to watch the proving process. So here we will draw like a diagram to show the relationship between A and B. And note that if we want to take A union with B, it is also equals to the B minus A part, which is this part, union with A. So it's this part. So that's like a pairwise disjoint set, and their union is the same as A union with B. So hence we can know this property, which is to say the probability of A union with B is equal to B minus A plus P of A. And this is also the same as to say like PB, the PB minus A intersection with B plus PA. So why this is correct? So why this is correct? And this is because if when we say B minus A, it doesn't have any like any component outside of A. It's B minus the part like it's B minus the part of B that is also in A, but it doesn't contain any parts that is outside of B. So this is possible. So that's the reasoning. And also we apply the second property here. We apply the second property to this equation, and we'll notice that because A intersection B is belong to B, then the probability of B minus A intersection with B, which is this is equal to the PB minus the PA intersection with B. And we combine this together, we'll get combine this equation and this equation, these two equations together, we get A union with B is equal to PA here plus PB minus PA intersection with B. And from now on, we have done the proof of all the property here. So this process is still relatively simple for some of the proof in later of this course. So I hope you can like pay attention to this and try your best to understand the process, and even without like pause the video and write the proof by yourself, and later to see if your proof is reasonable. Yeah, that's a good way to practice for proof. Usually like not always look for others answers first, and then to try to like memory the process, or try to convince yourself, yeah, his process is correct. But usually we can start by ourselves, and if we really prove that we have like others will agree with us at least, and that's a really wonderful process. And there's another property, it's called the continuity of probability measures. What does that mean? That means it's a really interesting topic, and we can see the diagram here for more understanding. So when here is a sequence of set A1, A2, A3 to A infinity. And here we want to denote A1 is a subset of A2, and A2 is a subset of A3, and A3 is a subset of like the next term. So here we define as like for any natural number k, ak is a subset of ak plus 1. So that's a way to express this phenomenon. And what's the property of this this kind of like a one layer set? So if like A1, A2 to the A infinity is an increasing sequence of events, which is illustrated by this diagram, then we can have one property, that is the limit of n goes to infinity of P an. So that is like the infinity term of A, which is here's we use a limit to express that, is equal to the probability of the union of all of the AK, which is the set before the n, and including that term. So from this diagram, it's not like very hard to understand, because the A is always the largest one. So so this term will equal to the probability of an at first, and because the union of all sets before the term an is just an, so that's the case. And for the second property, the decreasing sequence of event, which means like B1 is the largest set and B2 is a subset of B1. So in this process, we describe as for any k belongs to natural numbers, the bk is the bk plus 1 is a subset of bk. So goes to infinity, B will be pretty small, but also it can also represent the set of the original set, because the subset can be equal. So this is flexible. B can be small, B can be large. It's just at the A here. A can be, the A infinity can also be like the same as the A1 here, but it can also be like the universe set. It's not for sure. And here it means when n goes to infinity, the probability of Bn is equal to the probability of the intersection of all the B sets before and equal to n. This is also illustrated by the graph, because we can see when n goes to infinity, the probability of Bn is equal to the last term of B, and this term is also the intersection of all the sets, because all of the sets are greater than that. So it will not influence the the intersection of them will not influence the existence of the final set, which is the Bn itself. So this property is also said. These two, I would say these two theorem is called the continuity from above and below. This property, as I remember, is not used very frequently in later courses. Maybe you will never see them again. But it's also an interesting topic because I would say the graph and the property is they look unique. They look unique. They just like subset of one of another, and they are in a sequence. This is I would say this is unique for me. So I want to illustrate that. And also this property might have some application in real analysis course. So if you are also studying math, and you will see them later in real analysis courses. And if you are interested in, and I want to start a proof of the first process of this process. So how to prove that is correct? So first, the property we want to show is here, and we will define some new sets like D0, D1, D2, D infinity, something like that. And we define the D0 equal to empty set. D1 is A1, and D2 is not A1. So with this property, it means for all k greater or equal to 2, the dk is the ak minus a k minus 1. So this is so from now on, I know what is D mean. D means difference. It's like the difference between this term and the previous term. So in this case, D2 is equal to A2 minus A1, and D3 is equal to A3 minus A2. And thus, it is very obvious that all of the D1, D2, D3, D4, those D are disjoint sets. The collection of all D is also disjoint. This is so why that is true is very similar to some of the proof before. And to save the time, I will not show the details here, but the main logic, this is not the main logic of this proof. So usually the mathematician will neglect those out to leave space for more important process during the proof. So that will not be if you always list all of the proofs in details out, some proof might be like hundreds or even thousands of the pages, and is unable to read in one sitting. So in this case, we assume like you already understand that is true. So we are not need to prove that. We just prove those are disjoint, and because they are disjoint, this property, the intersection is equal to the empty set, and as a result, the union of the D is equal to the union of the K, which is AK minus A K minus 1, and this set is equal to AN. And this you may read as a U, but that is I would say I also learned from Professor Giersen before. Like this is a German way, like a Germanese way to write N. And if they want to write U, they'll be longer. And if they, you may say, oh, that's a mu, right? So if they want to write mu, they will put a like horizontal line below that. And if you want to write, so you may ask, what's the difference between mu and W? So the W, they just have one more curve. So they have the usual W we write is like this, and the German way to write W is like this. So just one more curve. So I will read this as N, but if you want to interpret it as U, that's totally okay. And because those are like intersection, we use the property. I mean, they're like pairwise disjoint. I'll use the property. Let me see here. So it's the sum. It's a sum, which is equal to the so which is to the AN itself. And here we will show that the AN is also the union of the decay from 1 to infinity is also the union set of AK from 1 to infinity, because dk is just like a pairwise disjoint version of AK, and their element is exactly the same. So by those property, now we have limit of n goes to infinity. The PAN is equal to the lim n goes to infinity P union union of like the first n terms of D, and that is by the property of 2 here, as this equation suggests. And this is also equal to the sum of all of the P decay, which is the previous process we just see. And this is also equal to the P decay, the sum of like 1 to infinity, because we can just replace the n by infinity by moving the limit out. And here, this one will be equal to this property. Why? Because those are pairwise disjoint. So use the property from above again. So previously we convert like to the union to sum, and now we convert sum to union. So this is the same as this set, and because we have the property here, we already proved this statement with the 3 stars, and now we can move the dk to AK, and we, as we look back, we'll see the whole process is just the same as the statement here. So we're done the proof. And for the second proof, if you are really interested in that, you can prove by yourself. So that can be a good way to practice, I would say. It's similar to the first one, but slightly different, as the process is not increasing but decreasing. So there's another interesting topic I want to talk about. It's like monkey typing Shakespeare's oval. That is like there's a famous like infinite monkey theorem. If you let a group of monkey, it can be very large group of monkey, and they are sitting before some typewriter keyboards, and they are typed for a very long time, many times longer than the time from now to the Big Bang time. So that's you can treat as the longest finite time, and sooner or later, with probably 1, you will definitely get a Shakespeare's oval out, and that's the infinite monkey theorem. So now we want to prove another version of this theorem. That is, we are not going to prove the exact Shakespeare's oval, but we want to prove how you will toast any given sequence of S of heads and tails. That is to turn cones infinitely many times. Like here, it's a sequence of like tail head or like any possible outcome there, and it's infinite, so it doesn't have a specific number of step. And we want to see if we can get any sequence of S of heads and tails out from this process. So first of all, let's consider sequence of tone flipped and partition it into groups of length k. So so the S1 will be length k, S2 will be length k, S3 will be length k, S4 will be length k. And there's also S5, S6, S infinity, because k is already limited, k elements, but the whole number of steps is infinite. So definitely there will be infinite S set. So now we define set AN as the S turn up how to interpret that? It's like the S turns up in the first NK ptosis. So S can be S can be any of the ptosis there, S can be any of the set before nk, but another set is Bn, which is the S is in the first n groups of the k. So what's the difference between An and Bn? So that is to say An can be, so we just the nk is a very large set, it's n times k, and which means the first n terms of S1 to Sn, and you can partition any set of any sequence of length k in that set. But for Bn, it's not, you can partition any set out. It's in the regular partitioning like S1, S2. So one of those partitions will be the ideal result. So that's the difference between the definition of these two sets. In a more obvious way, you say that. And here, we'll calculate the probability of S turns up. Turns up means the S is actually like the ideal term we define here will be find out. So here, the probability is equal to the union of all of the An set, like n is from 1 to infinity, and it's equal to the limit of n goes to infinity p an, and then it must be greater than n goes to infinity p bn. So why this case is it must be true, like the bn must be greater than an must be greater than or equal to an, because bn is a subset of an. Because if you can partition those set out, you can also find a partition of like S to here, but it has more choices. So definitely Bn has a smaller set of An. So this we already prove out, like the Bn is smaller or equal to the Pan if n goes to infinity. So now I want to find what's Bn. So Bn is Bn here is we first consider the complement of Bn. So Bn can be there are some elements inside Bn. It can be S1 not equal to S, S2 not equal to S, Sn not equal to S, but at least one set, like at least one set is equal to S that is not inside the whole term of Si, the first Sn terms is out of that. So we consider Bn complement happens when all of the subset we find out that is actually S is not in those previous S. So in this case, we'll say if we say like B and the complement is belong to the omega, then the omega n is equal to the sequence of length k, which is which means it's S1 S1 to the Sn. Those are the possible element inside the omega, which is the sample space. So give you some minute to think about that. The omega is like all of the it's all of the S1 to Sn, and they can be any permutation of that inside. So as a result, calculate the cardinality of omega, and we can find omega n. The probability is equal to 2 to the k to the power of n. So it's the 2k times n. So 2k here is 2k here is because S have k result, so it's 2k. And because here each case have n terms, so it's to the power of n. So that's like 2 levels. It's a nested power. So we found out it's 2 to the power of n times k. And now for the cardinality of Bn complement is equal to 2 to the power of k and minus 1 time and to the power of n. This is because B is the Bn complement is all of this is like all of that here, but at least they cannot be S. They cannot be S. So this is why we minus 1 here. If it's belong to S, then it's in B, it's not in the B complement. So that's the subtlety of this question. And if we minus 1, and that will be very similar to this term. It just have one cardinality difference. And then we times the power of n to represent their like n terms of the elements inside the set B complement. And now if we add on the limitation of n goes to infinity, like 1 minus the p, the power, the probability of B complement. This is same as 1 minus the probability of B. We just like to transform the limit outside of this large bracket into this small bracket. And why we want to calculate the 1 minus P B complement? This is the same as the probability of B. So remember, like the complement is equal to 1 minus the original set, right? So here, so what does this term mean? This term is the cardinality, the sample size of B complement divided by the probability of the omega, which is the same as saying 2 to the k minus 1 to the power of n divided by 2 to the power of k times n. So here, but what is this term when n goes to infinity? This need a little bit of algebra to calculate out. And finally, we can subtract n out and find it's actually 1 minus this term. And when n goes to infinity, 1 minus 2 to the power of negative k is really close to say it's close to 1. So this is equal to this will be close to 1, but because k is a positive number, so this term is a negative number. It's a positive number. It's a smaller than 1, but it's positive number. So this term will be smaller to 1, obviously. And when the smaller to 1 term times infinite time, it will all go to 0. So it's 1 minus 0, and the final answer is 1. Okay, so the proof is done with like you will get property 1 to actually get a sequence of the tails and head with when you have infinite time to compute that out. And this is like this example is really advanced for what we already learned right now. So if you are not totally understand that, it's okay. We'll discuss about like ERN models, the 4 type of ERN models next week. And based on ERN, if you like understand ERN models, you might have more thought about why those terms are workable, especially for the partition of the whole set into different S. So that might be helpful understanding if we go through next and possibly the next and the next week's lecture. So I'll get better understanding of that. So and also for this definition, the continuity of probability is also much more advanced than the level we're currently studying. So the most important thing you'll get from this lecture is what's a probability measure and what's the sigma algebra and some properties related to that. So that's the purpose for today's lecture.